Morning, everybody.
Good morning.
Sorry about Tuesday. That was really unexpected. I was getting set up to get ready for class, and all of a sudden I realized there was no power. And I looked up and it was like 10:28. So I had to really fast figure out a way to send you guys a message. I sent it from my phone. And anyway, so okay, so there were a couple of complicating factors. So I said that I was going to record a lecture and leave that for you from Tuesday, finishing off the igneous rocks. Well, I started that too, but this week is also the annual meeting of the Geological Society of America. And that's normally a week that I would travel and take off, cancel class, etc., and go somewhere. This year it was supposed to be in Montreal, Canada. That's who's hosting the meeting right now, but it's completely online instead because nobody can travel. So I've been juggling trying to listen to those presentations because it's a series of talks. They give short talks, like 15 minutes, and then you get time to ask questions, and then there's discussion periods at the ends of these sessions. Anyway, I can't do everything. So I decided I would just call it even, just give you guys a break, cancel the Tuesday class like we did, and I'm going to give you the rest of the igneous rocks lecture today. And we'll finish off metamorphism and sedimentary rocks next week. It'll be fine. So, and I figured you guys wouldn't complain if you had less work to do this week, right? Probably. I am, so this week is, the end of this week is the when you should submit your minerals labs, and I hope that that's going all right. I'm not quite done with the igneous. I've combined the igneous and metamorphic rocks into a single lab, and I'm nearly done with that. The document, I just need to write up the step-by-step processes for you guys. And I figure this time, instead of sending out a preliminary version and then updating it, which caused some confusion, I would instead I'll just hold this back and I'll post it later after class today so that you can grab it when you're ready after you finish the minerals lab. But let's see, it's not super long. What I've asked you to do in the igneous and metamorphic rocks lab is to identify 10 igneous rocks only, and 5 metamorphic rocks, and then to match 5 protoliths. These are parent rocks to the metamorphic rocks. I've got a fuzz on my nose. So you'll figure out what the metamorphic rocks are, and then in the process of doing that, you should understand what they're comprised of, what they're composed of, and that will help you to match them to their parent rock, the original rock type before they were subjected to increased pressure and temperature. Now, I realize that you haven't heard that lecture yet, but you've got your text to refer to. And honestly, the introductory information in the lab and on the website is enough to do the Metamorphic Rocks lab, so you should be all right. And I threw in 2 metamorphic minerals that I thought I would give you a shot at identifying. One is in the visual bank of minerals that you had, but it wasn't in your lab. The other one also wasn't in your lab, but it's not in the bank, and I'm hoping that you'll be able to figure it out with a little Googling. I'll see if I can find a resource of a page that, like, has it amongst other minerals and maybe help you spot it that way. Are there any questions about labs that you're doing now? I hope that that last version of the minerals lab was clear in all the steps that I wanted you to do. I'll just give you a second. Ooh, I'm getting thumbs up. Okay, cool. Okay. All right, if there are no questions, then let us proceed. So like always, I spend so much time like working on this class. Like, you know, you guys know that this is the first time that I've taught this class, or maybe you've forgotten, but it is. And it's a lot of work to put a new class together. And that's fine. I mean, I enjoy it. I spend so much time doing it because I'm having fun. I'm having fun putting it together and thinking about all the stuff that you guys need to learn, like what it is I think that's most important. And also I want to give you the stuff that I think is fun to learn too. All right, I'm sort of juggling Zoom windows and trying to find my lecture here. I wish the Zoom windows didn't cover up everything else on the screen. Okay. I also updated the PDF version of this lecture. What is that? Oh, that's the wrong one. Sorry, I grabbed the wrong one. So I updated the PDF version to match the final version of this lecture. I even updated some of the slides that you've already seen, but just a little bit, so you don't have to worry about redoing those. Okay, and let me share the screen. Okay. I'm going to scroll down. We are something like, I put a marker slide here, part 3. Okay, so we've got a lot of pictures to look at. So even though there are a number of slides to go through, they should go rather quickly. All right, I'm going to pick up where we left off with composite volcanoes. I showed you this picture of 3 different kinds of typical, I keep saying composite volcanoes and I mean to say stratovolcano. They're related, right? A stratovolcano is one of these. It's a single vent, so a single crater on a single volcano. That's a stratovolcano that forms at a subduction zone boundary, like an ocean continent subduction zone boundary, as a result of partial melting of the mantle as that subducting slab goes down deep into the mantle. A composite volcano is a stratovolcano that's got other vents on it, basically. It's got other subvolcanoes like cinder cones, or maybe a second vent on the same stratovolcano. So they form in the same places, they form by the same processes. So that's why I'm kind of using them interchangeably. The composite, as the name suggests, means that it's comprised of more than one type of volcano. Okay. So these pointy peaked volcanoes that often are snow capped, like Mount Fuji is, I don't have that here, but you know, if it weren't so warm in the Philippines, that would have snow on top there too. Okay, so this kind of setting. So I'm going to say it again because I want to make sure everybody understands this. The subducting slab drags down sediments, water, and also minerals within the subducting crust and lithosphere that give off water. that's buoyant. It rises in the mantle, into the mantle that's above that subducting slab. So we call this bit, this part of the mantle, the mantle wedge, because it's a little wedge that sticks here above the subducting slab and underneath the continent. It's right there in that wedge where the water rises up. It lowers the melting temperature of the mantle. And I found some diagrams to explain this finally. I wasn't showing you that because the diagram I had was too much. It was just too much. So I had to find something just a little simpler so to get the concept across, because I want this concept of the water lowering that melting temperature to come across to you guys. So that's at the very end. Okay, so we lower and this is called flux melting. That's the name of this. Like decompression melting is the name of the melting that you get under the mid-ocean ridges and under continental rifts. This is called flux melting, which is the flux is the movement of the water into the mantle, and that water then lowers the melting temperature. Okay, so it's just a slight change, and then you can melt just a little bit of that ultramafic rock to get a basaltic magma. And those magmas are also buoyant, like the water. It rises up into the overlying crust. And then it doesn't stay basaltic. It transforms by a process we call differentiation, magmatic differentiation. I've got slides on this near the end too, that will explain how the different ways that you can get continental crust or different magmas being added to this basaltic magma to change it so that it turns out andesitic in composition, intermediate in composition instead of mafic, or maybe even rhyolitic. So at these composite volcanoes, or I did it again, stratovolcanoes, you're expecting an andesite or a rhyolite composition, right? Not basaltic, because that melt had to pass through this thick continental lithosphere first, right? In the other situations, in a mid-ocean ridge and a continental rift, the crust is thinned and it's either passing through oceanic crust already, or it's coming up in the middle of oceanic crust. So it's just all basaltic, or it's passing through very little continent, and then it's unchanged in the case of the continental rifts, like the Basin Range or East Africa. All right, I'm going to keep moving before I give the whole lecture on that single slide. Okay, lava domes. I promised you that rhyolitic lavas are viscous, right? Viscosity. Let me give you a couple of examples. So water is not viscous. Water is runny, and it runs off a slope easily. But if you compare water to different liquids like honey is thick and syrupy, right? Or syrup or molasses or any of those things. It's viscous compared to water. That means viscosity is a weird word because it means like it doesn't do something. It resists flow. It's not flowing well. So honey is viscous, water is not. The rhyolitic magmas and lavas are viscous. They're thick and sticky compared to basaltic magmas and lavas. So when you erupt a rhyolitic lava like this, it forms this steep-sided dome structure because the lavas haven't gone anywhere. They're so thick and sticky that they don't flow. They're just stuck in place, and you get these domes. So this is a frequent feature, these lava domes, that where they come up in the center of craters. So at the tops of volcanoes, after an eruption, after a big eruption, you often get these lava domes coming up. It's like the last little bit of magma that reaches the surface and it blurps out. And that was its last little hurrah for that eruption. So it's a common feature in these craters. I showed you an example in Mount St. Helens before. Here's a different image. And you can see this because remember, the 1980 eruption blew out. There's a landslide on the side of the mountain, and then it was a lateral blast. So we lost part of the side of the volcano. And now we have this nice view into the lava dome. It doesn't look like this anymore, though. There's a camera, there's a webcam in Mount St. Helens's crater that you can go get. It's often in the clouds because it's Washington, but you can like go see what it looks like on any given day. The steam is not just steam, meaning water vapor. It's composed of all the different volcanic gases that we talked about, but water is the largest component, right? Carbon dioxide would be the next, and then probably sulfur dioxide, and then fluorine and chlorine and other compounds like that. There's some acids in there too, because if you combine carbon dioxide and water, you get carbonic acids, or sulfur dioxide and water, you get sulfuric acid, chlorine and water, hydrochloric acid. And those are some of the gases that I was describing when I went out on above that lava tube in Hawaii, and those gases were stinging my nose. Those were the acids doing that. Okay, and remember, rhyolitic magmas also have more gas in them too. Okay, so when the lavas that we've been talking about are effusive eruptions, right? They're not explosive. They are eruptions of lava onto the surface. It's generally pretty peaceful, but explosive eruptions are common in stratovolcanoes. I got it right that time. And the way that we name the materials, the pyroclastic materials that come out of an explosive eruption, depends on their size. So the particle size, these are ash-sized particles of rock. If you look under a microscope, or actually you need like a scanning electron microscope, you can see that these are jagged, sharp, glassy pieces of rock. And they're very abrasive. The ash, because it's rock and not just like ash that comes out of your fireplace that's soft and fluffy, it's not like that at all. Is that the reason flights get canceled when there are big eruptions, like from Europe to North America after the last really large eruption of an Icelandic volcano, or oftentimes it'll be an Aleutian or an Alaskan volcano will erupt, and then the flights that go from North America to Asia get canceled because they follow a great circle. So they go north is the shortest route instead of following a latitude. So they have to stop flying because they don't want to encounter an ash cloud, because the ash cloud will, the ash itself will damage the blades, will it'll braid the windows so that the pilots can't see. It does a number. And it wasn't actually until like the early 1980s that we realized how dangerous volcanic eruptions were to airline flights either. I'll tell you a story another time, but it was a British Airways flight over Jakarta, I think, Indonesia. And it was an Indonesian volcano that erupted, and this flight almost crashed. But they managed to get back down, and the pictures of the damage to the plane are just incredible. And it was all from flying through an ash cloud. Anyway, I'm getting off on a tangent again. Ash-sized particles are 2 millimeters or less, so they're tiny. Lapilli are these pea-sized particles. There's a dime for scale. And these three, ash, lapilli, and then bombs are hunks of semi-molten or molten rock that are erupted out of the volcano. So this is new material that's it's new lava that's been erupted, and it's like splattering out of the volcano. And these things tend to fall fairly closely to the volcano. The larger the particle, the closer to the volcano it falls, just because of gravity. And these are all considered airfall fragments. There's a counterpart to the bombs, and that's called a block. A block is simply a hunk of rock that came out solid. And oftentimes it's not a new piece of magma or lava that's erupted. It's a piece of the volcano that was pre-existing that gets shot up into the air along with the new material. I'll give you, oh, it's here. That was handy. Okay, so here's the categorization. There's ash that are the smallest fragments, lapilli that are between 2 millimeters and 64 millimeters is 6.4 centimeters. It's probably something like this. It's definitely smaller than your fist. Blocks and bombs are larger, or fist size or larger, I'd say. And the difference is being simply that the bombs are deformed. They're kind of football shaped. They're streamlined as they flew through the air, and blocks are solid. And we can get these airfall fragments fall on the ground, and they can end up sort of acting like sediments, because over time they can become lithified into pyroclastic rocks, and then we can name them using this scheme down here, these two triangles. And I'll just point to a couple of things. I don't want you to learn how to do this at all. I'll just show you that you start on this triangle using ash-sized particles on one corner, lapilli on this corner, and blocks and bombs on this corner. And then this is how you name the rock, the pyroclastic rock. And most of them are tuffs. That means that most of the rock is made up of ash. That's the largest volume of new material that's erupted in these explosive eruptions anyway. So it makes sense. So they have like an ash matrix. And then tuffs can be further broken down this way. Either they have glass particles in them, or crystals of different minerals, or rock fragments. And so oftentimes you'll have like a lithic tuff is one that it's mostly ash, but it's got pieces of lapilli and blocks and bombs in it too. And it's lithified into a rock that way. So you can almost think of it as like a sandstone with different size rocks in it, kind of, except that instead of sand, it's ash. Anyway, so there are two different things going on here. In this box are the pyroclastic rocks. Maybe I should write that. These are pyroclastic rocks. I'm going to make that black so that you can see it. And then we're going to put that here. Okay, pyroclastic rocks. Okay. So this is how you name those pyroclastic rocks, and this is how you name the individual airfall fragments. Okay? Questions about how we do this? I'll show you some pictures of tuff as we go. I want to show you some of the kinds of features or processes that take place during these eruptions and during these explosive eruptions. I said that ash and volcanic gases are the vast majority of what's erupted out of volcanoes. And we looked at a diagram that showed that water was the most voluminous vapor or volatile. It's the largest amount of any of the gases, the volcanic gases. Carbon dioxide is second. Then it's nitrogen and sulfur dioxide. I forgot about nitrogen. So yeah, there are greenhouse gases in here too, right? But even though this is a misconception that students often have, even though a lot of these gases contribute to greenhouse gases, like nitrogen, there are different number of like NOx, NOx, nitrogen compounds, or sulfur dioxide, sulfur compounds, carbon compounds. Um, Volcanic eruptions don't increase global temperatures. The very large eruptions actually decrease global temperatures. Do you have any guess why? If those volcanic gases are contributing to global warming gases, you'd think it'd be warming, but it doesn't. It cools global temperatures. Why do you think?
Is it cool if I answer?
Of course.
A lot of it is because the ash blocks out the visibility of the sun, and so the sun rays can't reach the Earth's surface, and it cools the temperature.
Yes, although, check it out. The ash doesn't last very long. How long do you think ash stays suspended? Anybody can answer, but Kay, you're welcome to answer. How long do you think ash stays suspended in the atmosphere?
Well, I mean, can't it depend upon the size of the eruption?
Of course. But like I said, ash-sized particles, the larger the particle, the faster it drops to the earth because of gravity.
Mm-hmm.
So it doesn't stay suspended forever. I would say on the order, I mean, some ash falls right away, but I'm talking about the stuff that lingers. It can linger in the atmosphere for days or even weeks. But to cool global to cause the global decrease in temperatures, we actually need that to last longer than that. But the ash helps do exactly what you're describing. The volcanic gases, though, actually, the molecules that are suspended, I mean, they're aerosols. The aerosols that are invisible to us. So not just the ash, the gases that make up those compounds stay suspended for even longer. And so what happens is those aerosols also reflect back solar energy. So it's ash and the aerosols made up of these gases that stay up in the atmosphere. And then you can get decrease like up to a degree Celsius for like 5 years in the very large eruptions, like a Krakatoa, a Tambora, those historic eruptions that had, it was Tambora, that eruption in 1882, 3 or 4. It was 1882, 3 or 4. I can't remember exactly. But do you know that painting, Edvard Munch's painting of the Scream? It's all orange and it's like a bald guy in a blue pants and he's like this. I'll dig it up for you sometime. He painted that in Norway, and Tambora is in Indonesia, in near the equator in Asia. And Edvard Munch painted this orange sky that was happening in like essentially in the Arctic a couple of years, or it was a year or two after the eruption of Tambora. He painted these orange skies that resulted after that large eruption because of that was the ash filtering sunlight and creating these orange skies. Remember how we had the orange, or if you're in Northern California, we had an orange sky last month because there was so much ash in the air. It was like that. But it was seen around the world that the eruption was so large. So my point was that there are far-reaching effects of these large eruptions. So Arctic Norway, they were painting about it and seeing those orange skies that far away from an eruption near the equator. And it's unclear whether he painted that from memory or if the orange skies lasted for a long time. Here's Pinatubo in the Philippines in 1991. One of the first stages of large eruptions is a large ash eruption. And these are explosive, so they go straight up into the air oftentimes out of the crater. So this is, notice that this is gray. And I showed you this picture of Mount St. Helens and I talked about steam here. This is white, right? There's a difference there. This is white, or a white cloud. That means that it's just gases, volcanic gases and steam. When the cloud is gray, that means there's rock involved. There's new magma that's being erupted. So that's an important difference. So even here, even though that kind of looks like clouds, these must be volcanic gases here. So there are volcanic gases coming up too. And if there was a lake at the bottom of that crater or something, that would have also flashed to steam during this eruption. But the fact that it's a gray cloud tells you that there's new magma erupted, new lava erupted, and that's actually rock, right? Ash is tiny particles of rock. Okay, Pinatubo. No, that was it. Let's go to this picture of Mayon in the Philippines. Ash, like I said, is the most common type of eruption. This image shows like 4 different pyroclastic flows. Here's one. They look like avalanches. There's another one. Here's another big one. These are essentially large avalanches of volcanic ash, gas, blocks and bombs. They pick up trees and other rocks and whatever's on the surface, and they move downhill really fast, and they're really hot. So they first they burn everything in their path. They knock down everything in their path. Certainly in the first few kilometers, they're knocking things down. They're traveling like 500 kilometers an hour. They're moving really fast. You can't outdrive them. You certainly can't outwalk them. And because they're so hot, you also can't protect yourself against them. So these are deadly. The other deadly hazard that, so I'm talking about hazards now too, volcanic hazards. So ash can be a hazard because it can land on the ground, it can ruin crops, it can kill livestock, it can collapse roofs if there's too much ash. It's heavy, it's rock, so it can collapse buildings. So it's a hazard. But the pyroclastic flows are traveling. They move down these valleys rapidly, and so do lahars. These are more like, these are like rivers of cement almost. They're thick. It looks muddy, but a lot of this is ash and new material. So what happens is one of these hot eruptions, ash is landing and hot blocks and things are landing close to the volcano. If there's snow on the volcano or a glacier up high, it's going to land on that ice or water, and it's going to mix or melt the ice and cause like essentially like a flash flood. And it's carrying everything with it. And because it's thicker than water, so it's more viscous, but it still can move very fast and rip up giant boulders. I encourage you to get lost in some Lahar videos on YouTube sometime and just watch some of these. They're spectacular. Just go check it out. But these are moving, they move, pyroclastic flows and lahars move kilometers from the volcano, from their source. So, and because they're adding a lot of volume to creeks, they can take out bridges or erode the side channels of the stream beds or the rivers. And I've seen houses floating in mud flows like this. That's something else you can find on YouTube, is a house floating in a lahar. Okay, I think I'm done talking about that. Here's a block. Some of them are very large. These don't go very far though, right? Because they're big. There are other blocks out here too. So these are what, if you're on the top of a volcano, these are some of what rained down on your head. Oh, this reminds me, for part of your Igneous Rocks lab, I'm going to assign another video, because there are some great, like I've been talking about videos of Lahars. There's some great videos just showing different volcanic hazards. So I'm going to assign one or a few small ones, and then give you a list of other recommendations, because they're just some great videos to watch, period. Okay. This is a cinder cone that I visited in Argentina, and I'm up on the side of the cinder cone, and there are a bunch of cinder cones out here. It's just a whole field of cinder cones. They're smallish features. You see the craters up at the top there. And what do you notice about the material that's laid down on the ground? Look at how it changes about at the road. I've drawn a white line where I see the ends of the end of the blocks and the bombs coming down, and then it's just ash and lapilli. So the ground is made up of ash-sized particles and lapilli-sized particles. It's gravelly. Most of the ash was gonna like filter down and kind of be lower down, but the lapilli forms like a gravelly surface, and then you've got big chunks of blocks and bombs that are around, but those don't travel as far, so they end sort of about here, and then it's just ash and lapilli. So I'm just trying to demonstrate with that image that it doesn't go far. You may run across the term tephra. That tephra is a word to describe all of the airfall fragments. So if you run across that, that's all it means. Okay, please stop me if there are questions. All right, I've got a couple of things I want you to do. This one I'll make individual. I'm going to put you in some breakout groups today just to think about some of these things. I want you to look at this image and just take a second while I'm talking, think about it. Does anyone recognize this volcano? No? It's in California. You don't always see it from this direction, so it looks a little different.
Is it Shasta?
It is. Good one. So if you're driving up to Northern California on Highway 5, you'll pass Shasta very close to the highway. Yeah, good spotting. What I want you to do though is, what are the different volcanic landforms? What are the different features that you see on this landscape? I've got the chat window open. If you want to list anything in the chat window that you see, name a landform or name a feature that you can identify. I mean, this is all solidified rock now, right? But some of it looks like it's moved too. There are definite features of flow. Feel free to shout it out if you see anything, and tell me where you see it. Can you tell me, is Shasta a strato? Would you call it, is it better named a stratovolcano or a composite volcano? A lava dome, someone says. Yes. Where do you see the lava dome? On the left corner. Sorry, it says on the left corner. I couldn't see that part. Left corner. There's the lava dome right there. Good spotting. What else do you see?
Possibly a pyroclastic flow, all that black stuff, something
Lava
that flowed
flow.
out.
Lava
Lava
flow.
flow.
It's black because guess its composition. I mean, it's black and white, so it's dark. I mean, we have to guess. But let's assume that the dark color in black and white means black in color. What does that tell you about the composition of that flow then? Or actually, never mind the color. Just look at how far it's moved from the volcano compared to the lava dome. I mean, this hasn't moved from the crater, but this lava flow has. It's moved at least from here to here. And look at how far this has gone. Nowhere. It's just there. So this has to be less viscous than this. So you could tell me, you could give me a good guess about the composition of the magma or the lava that formed the lava dome, and you can give me a guess about the composition of the lava that formed this flow. And if you don't know, you should be asking me a question right now. What other features do you see? Basic features. How about a crater? Any craters? I mean, you can't see the inside, but up here, the vent or the crater for the top at the top of Shasta is the main vent. What about this thing? And no one's answered my question about whether stratovolcano or composite volcano is a better name. This is what I'm talking about as like a parasitic cone or like an additional eruptive center. Someone was about to say something.
Is it a stratovolcano?
It is, but I think composite is a more accurate term because of this feature, because it's not just one cone. There are other eruptive centers. So this it was erupting on its flank too. So there may have been more than one magma body feeding this, or I suppose it could have changed over time. But this is what makes it a composite volcano, is the fact that it's got multiple eruptive centers on it. Okay, those are the things that I wanted you to see: the lava dome, the flow. There are some other things like these lumps could be really old cinder cones that are now just really rounded, or they could be a result of landslides or old pyroclastic flows. So the lumpy, bumpy land surface can be landslides. It could be a pyroclastic flow, but I'm not sure. So I didn't expect you to pick that out. All right, good job. This one is real, even though it looks like a cartoon. I wanted to find another landscape where we could do this exercise. And I wonder if you can say anything about this landscape. This is Kamchatka Peninsula. So this is northeastern Russia. And I just want you to tell me about what do you see in this one?
I see a little parasitic volcano
What does it
at
look like?
the base of it. It's a little darker and you can see a little bit of red.
Right there.
Yeah, right there. Yeah.
Nice. Yeah, exactly. There's one. So that's actually, that's a different kind of volcano name.
Cinder
Do you want to
cone?
guess?
Cinder cone?
A cinder cone, yes. And the reason it's dark is because cinder cones erupt basaltic magmas. Yep. Even though it's on the flank of a composite dome. Well, shoot, we were just talking about a basaltic flow here coming out of Shasta that we know is a strato/composite volcano, right? So it's definitely possible to get basalts out of these volcanoes. It's just not the vast majority. What else do you see in that on the landscape?
I have a question.
Yes.
Can one type of volcano erupt different, like slightly different compositions of magma depending upon the eruption, or are they consistent in the composition?
The composition changes depending on whatever the magma composition is. So whatever is going on in the plumbing system underneath the volcano is going to change the composition. So if you can get like new pulses of magma coming up and feeding that same magma chamber. And so over time, you might see changes to the composition coming out of the same crater, the same volcanic center. Absolutely, that's possible. It's also possible to get like dikes coming up or veins coming up of lava from that magma chamber and feeding the flanks, like maybe something like this. It was another little feeder dike that got, maybe that never interacted with the original magma chamber at all. Um, there's another little parasitic dome there. I'm not sure what that is right now. But there are a bunch of different, like that could be a cinder cone. There's another cinder cone, but there are multiple volcanoes in this landscape, right? There's a composite volcano, because I'm going to count these things as part of it. Composite volcano, a stratovolcano behind it. There's another one to the left. Those in the distance are also stratovolcanoes. I was hoping you guys would see this lava flow, and I'm sure some of you did and just didn't say anything. I wish you had said something. What can you tell me about this lava flow?
The lava is most likely basaltic because of how far it goes.
Right, because it's pretty fluid. The lava was pretty fluid, and so it flowed a long distance. And do you notice how like it even got captured by this? There's a stream bed or something here, and it got captured there. So it started to flow down the stream bed instead of going across it. Yeah. Good. Okay. So that's those are the sorts of things that I hoped you would spot. Um, I put this together of a bunch of different landforms, just the same. I'm going to put you into breakout groups real quick, and I want you to decide what are the features in 1 through 9. I'm going to assign these randomly, okay? Let's hope I can remember how to do it. So come back to me in 5 minutes with answers for 1 through 9, and I'll ask you to volunteer. So hopefully somebody from each group will volunteer some of the names. Okay, breakout rooms. And how many are there of you today? Wait, I can't see. Like 15. Okay, I'll put you in 3. 1, 2, 3. I'll put you in 4 breakout groups. All right. Good luck. I'll see you in 5 minutes. I think you should be able to see the image from the breakout rooms. Or you please go to your breakout rooms. Click the button to go.
Excuse me, Professor. I went to the bathroom and I missed all the group stuff. Oh, and I can't hear you. You're muted.
How did I get muted? That's weird. Do you have a breakout room button that you can join?
Yes.
There you go. Go ahead and join them and you'll see what to do.
Okay.
Welcome back. As people are trickling in. Hopefully the rest will join us in just a second. Okay, I hope it went well. There's one more person we're waiting for. Come on, Marco. Okay, I think we're all back. Good. How did it go? What you got for me? Oh, let me share the screen again. I realize it's not sharing anymore. There we go. Okay. So, sorry, I guess you couldn't see the slides when you went to the breakout rooms, which is a pity. But at least a few of you got creative and went and found the slides on iLearn. So thank you for that. What did you guys come up with?
My group said that 1, 2, 6, 7, and 9 were lava domes.
1, 2, 6, 7, and 9 were lava domes. Partially correct. Does anyone else want to chime in on that?
Is 8 also a lava dome?
I think 8 probably is a lava dome. Yes. No, I know it is. I know it is. Now I remember which one it is. Correct. So we'll add 8 to the lava domes. But what about 1, 2, 6, 7, and 9? What? So I didn't see whose name. Who just volunteered 8? Can you? Do you want to tell me of 1, 2, 6, 7, and 9? Do you think there are other lava domes in there?
I think maybe like which one isn't a lava dome?
Which others are lava domes?
For sure, I think 2, 6, 7, 8, 9. I'm not sure about 1 though.
Yeah, 2. Okay, so I'm going to give you 2 and 8 are definitely lava domes. Okay, 1 is a lava dome. 6, 7, and 9 are not lava domes. So 1, 2, and 8 are lava domes. What are 6, 7, and 9? Does anyone have a different guess?
Can I pitch in?
Say that again.
6, 7, and 9 are cinder cones.
They are cinder cones. Yeah, right on. Okay, what else do you guys see in this image? We've got 3, 4, and 5 left. And I'm trying desperately to remember where 5 came from. Where did I get that one?
Is 3 and 4 a stratovolcano? Since
Yes,
there's only
3
one.
and 4 are stratovolcanoes. Those are easy, right?
Yeah.
Yes, and what about 5? I'm trying to remember myself, and without a scale, it's kind of hard. You know, without a scale, I don't remember if those are, they're not, they can't be cinder cones because the deposits are too light colored.
So composite volcanoes?
I think this must be a composite volcano. Yeah. There's one thing I want to point out. So good job, you guys. Great. And 6, 7, and 9, yeah, those are tricky. The one thing that you can see that differentiates them is, yes, they're kind of steep-sided, but they're more cone-shaped than they are steep-sided. Like the lava dome is just this part that has the steep sides, and just this part, not the crater, just the part coming up inside. So this is inside a crater. And these, the cinder cones contain a crater. See, they have a crater at the top. And they also, oftentimes you get basaltic lava flows from the base of cinder cones. So the top crater erupts the cinders, the ash, the lapilli, and the blocks and bombs. And the base erupts a basalt. So here's one coming out of the base of that cinder cone. There's another one coming out of the base of that cinder cone. So that's one way to differentiate them. Good, okay. We talked a little bit about hazards already, and I just wanted to use this slide as a way to summarize all the different hazards, okay? So first, let's talk about the ash cloud that's formed. So the eruption column goes up into the atmosphere, and you get an ash cloud that forms. I would call that an ash cloud, not an eruption cloud, but and that also brings with it volcanic gases, right? So there are gases mixed in there. And so it's the ash and the aerosols that get into the atmosphere from the gases that are erupted that also cause temperature decreases. Some of those gases contribute to global warming gases, right? And you can also get acid rain as a result of that. So that would, acid rain is just, it's any rain that's not a neutral pH 7, right? So it just needs a little bit of acidity to become erosive to things like marble headstones in a cemetery, or that's the first thing I can think of. it's going to erode limestone and marble because it's a gas, because it's made out of carbonate, it's made out of calcite, which you did in your labs, right? Hopefully you've already done in your labs. Okay, so the tephra or the ash and those like the lapilli blocks and bombs, all of that is a hazard if you're close to the volcano. The acid rain and the more far-reaching effects of the aerosols that we already discussed, those can be felt at farther distances, obviously. Lava domes, pyroclastic flows, here's another pyroclastic flow, landslides, because the landslide can trigger the eruption, not because the landslide itself is a volcanic process. Well, okay, it's related to volcanic processes, probably because of the seismicity that takes place around the volcano during the eruption, and while magma is moving around underneath the ground, that can cause shaking that might trigger a landslide, and then the landslide can trigger an eruption. Lahars, so these volcanic mud flows, lava flows, certainly. Lava flows usually are not as dangerous, right? Because you can usually outrun those unless you're on a hill. And it's a basaltic lava flow that happens to be pretty runny. The lahars, though, and the pyroclastic flows are the most dangerous, and they go the farthest, at least on the ground. The ash and those aerosols are the most common type of eruption, though. Okay, I just gave you the answers to a couple of quiz questions right there, right? So what are the two most dangerous volcanic hazards, and what's the most common volcanic product? Can you answer those now? I'll guess that that's a yes. All right, I'm going to do it to you again. Are you guys ready to look at these slides this time? Do you have the slides open? At least hopefully one per group. Well, tell me, did that work last time or did it not work?
It did work.
It did work.
It
So
worked.
Like,
go ahead, tell me.
oh, I was just gonna say that we opened our own slide and shared, and it worked perfectly.
Great. Okay. If you could do the same thing or keep that open, I want you to go look at this slide. And this time I want you to identify the volcanic, the type of volcanic hazard that you see in the image. Okay. So I'm going to put you in breakout groups. I'm going to make it 4 minutes this time, just because 5 minutes always seems like so long. And this has a few more things though. And I'm also gonna, let's see. So I want to, oh, I think I just assigned you again. There you go.
So just look at the volcanic features.
The hazard, what type of hazard are you seeing in the image?
Okay.
Of the ones we just listed, right? Please go to your rooms so that I can call you back shortly and finish the lecture.
Can you put me in my room again?
You have to click a button.
I know it went away.
It went away.
Yeah, I don't see another button.
I don't know how to do that. Let's see. Maybe I do.
Oh,
I'll
wait,
try.
here it is. Never mind. Okay.
Okay. Welcome back. I hope that that was a little bit more challenging and interesting. All right, folks are showing, oh, it's time. Okay, everybody's back now. Great. All right. How did this one go? What you got for me? You can still see my slides, right?
Yeah.
Okay, good. Oh, I didn't see, someone added a bunch of answers to the chat last time. Sorry, I didn't see that. Okay, so what do you think here? I see one vote for 5 and 10 being a Lahar. Yes, those are Lahars. So they're watching this Lahar come down a creek. You notice the logs, the tree logs that are in it. That's the clearest video capture I could get. So those are Lahars. What else do you see? And sometimes you can there are more than one answer depending on how you view the image. So don't worry about, okay, so we got 4, 7, and 10 pyroclastic flow. 4, 7, 10. Oh, 10 is a Lahar, but close.
He put in the chat 11. He didn't mean to say 10.
Oh, sorry, 11. Yes, 11. So 4, 7, 11 are pyroclastic flows. Exactly. Okay, so we've got, we need the top 3, 1, 2, 3. We need to figure out 6, 8, and 9.
Are 1 and 6 eruption column?
1 and 6. Yeah, the eruption column, the ash cloud, right? The eruption column is the feature. The ash cloud is the actual hazard. The ash is the hazard. Okay.
Number 3 is gases. And it looks like the rock probably has a lot of sulfur in it because it's all yellow.
Sulfur rich gases. Yes, exactly.
Are 2 and 9 lava flows?
2 is a lava flow, 9 is a lava flow. Okay, what about 8? That's probably the trickiest one.
Honestly, I thought A might have been eruption as well because it looked like it was going up as like an eruption cloud as well, but I wasn't sure.
Yeah, also there's lightning. That's what this is. I know that was hard to see, but ash clouds, because the particles are so small, they can become charged, ionized, and you get lightning as a result. So I thought I would throw that one in there as kind of a bonus. All right, good job. Okay, hopefully that woke you up a little bit. That was my intention, was to get you actively thinking about these things. Okay, what controls whether an eruption is peaceful or explosive? We talked about some of these things. I talked about the viscosity and the gases. Together, they work to make the difference between a peaceful lava flow or an explosive eruption. So number 1, the viscosity. If you've got low viscosity magma, a basaltic magma, it's less viscous, right? It flows easily. It doesn't have a lot of silica, so it doesn't have the tetrahedra getting in the way so that it can flow. It also, the fact that it doesn't have the silica tetrahedra means that it can allow the gases to escape gently, peacefully before the eruption. But in a stratovolcano with a rhyolitic or an andesitic magma, it's the high viscosity and the high amount of dissolved gases that cause it to be explosive. I should have added to dissolved gases, and I will just add, I'll say it also, come on, I'm trying to do this. I would also say what? I want to say that the volume of gas bubbles, this is giant, increases exponentially. Okay, so fix this real quick. 20. It increases exponentially, and so that can be cause explosiveness exponentially. Right, because we looked at that chart that brought when the magmas got much closer to the surface, when you took the pressure, the load of the overlying rock off of the magma, the gas bubbles increased in size rapidly. And so that caused the explosiveness. So the silica tetrahedra prevent a rhyolitic magma from letting the gas escape. And the gas, because there's more gas in there, it's going to increase in volume exponentially, making it explosive. Okay, the viscosity is controlled by a number of things. Temperature is one. So the hotter the magma, the less viscous. The cooler, the more viscous. Think about honey in this example. If you pull honey out of the cupboard, it oftentimes gets thick and sticky and crystallizes. Well, and you can't pour it at all. You got to put it in the microwave and heat it up before you can pour it. Same idea. You decrease the viscosity of the honey by heating it up. Same thing with the viscosity of the magma. You would decrease the viscosity of the magma with higher temperatures. The composition certainly affects it. That's where it relates to silica. Bubbles, the actual bubbles and any phenocrysts, right? So that's the phenocrysts. Those two things cause the magmas or the lavas to be more viscous. So they increase the viscosity. They just get in the way of the flow. Again, same, just like the silica tetrahedra in a way. The water content or the amount of volatiles. So volatiles is a term for the dissolved gases or all of the gases, not just water, right? And then pressure can have a tiny effect, but these four at the top are the major impacts on viscosity. Okay, this is a good slide to study before an exam because I explain exactly how viscosity is controlled. Okay, I wanted to I put this in here because I keep talking about the 1980 eruption, but I haven't shown you anything really yet except pictures of the existing volcano. Here's what it looked like before. This is a series of stills. There's no video because nobody was ready. We didn't all have video cameras in our pockets in 1980. So I was a kid, so I certainly didn't, but they took a bunch of pictures. So this is a picture. Okay, it goes like this: 1, 2, 3, 4, 5, 6. So this is the landslide happening. The side of the mountain starts to go. It slides down there. It goes even farther here. And what's left underneath, it almost looks like a lava dome. It's probably the magma. It's probably part lava dome, honestly. And the magma is very close to the surface at that point. Well, once that burden has been removed, all of that land was a pressure on that magma. Then you reduce the pressure by landsliding it away, and then you get the explosive eruption, right? Those gases expand rapidly, and then you get the giant explosion. And again, it's black, it's dark gray, meaning there's rock in there. It's not just steam. Okay, these are pyroclastic rocks. This is what, when you put all the tephra, when you put all those airfall fragments together and then make a rock out of it, lithify it into a rock, this is what it looks like. Pieces of blocks and bombs, lapilli, but most of it, the matrix is ash. This is another example. This is a series of eruptions, right? There's 1, 2, 3 eruptions represented there. with the, it almost looks like the eruption starts there. I would say the coarse stuff falls first and followed by fine. That's how it should be, unless it's inverted. Anyway, oh, that's true, because this is true. So the start of the eruption is the fine material, because that goes out farthest, and that's followed by the flow of the pyroclastic cloud, which is going to carry the coarser stuff. So that's one eruption cycle right there. Okay, so these are tuffs, or this one gets a special name, ignimbrite, just because it's from a pyroclastic flow. But you get the idea. It's mostly ash with a bunch of other particles, these particles. Okay, so I would call that rock a lithic tuff, because these are pieces of rock that make up the vast majority of it that's not ash sized. Okay, so it would be like one of these rock fragments plus mostly ash gives you a lithic tuff. Okay, here's another little close-up of what a tuff looks like. And in this one, you can see like individual crystals, but mostly like the matrix is like, it's almost blackish. It could be because this has almost a glassy matrix to it, because the ash-sized particles are, all of this is deposited hot, and ash-sized particles are so small that they can kind of remelt and you get a glassy matrix. Anyway, there are rock fragments in here too, and crystals. So you might end up calling this like a lithic crystal tuff or something like that. All right, craters versus calderas. You've probably heard the term caldera, and you certainly have seen craters already. This is Mount St. Helens' crater. It's relatively small. We're looking at maybe a 10,000 foot mountain, and it might have a crater that's a mile across, for example, I'd say at most. And yeah, and during an eruption, you're losing, you know, maybe 1,000 feet in a large eruption, maybe 1,000 feet off the top of a volcano. In very large eruptions, at super volcanoes like Yellowstone, or in this case, Mount Mazama is the ancient name of the volcano before Crater Lake existed. This is Crater Lake. This is an artist's rendering of what Mount Mazama must have looked like. That eruption was so large, it was like a Yellowstone type eruption, or a Tambora or Krakatoa, those global scale eruptions, huge. These eruptions are so large that the entire top of the mountain is blown off, and there's a void underneath that is left behind where all the rock used to be and magma. And the top of the volcano actually falls into itself. It collapses into itself. And it leaves behind a depression. And in this case, we're talking about something that's maybe 5 miles across instead of 1. And you're maybe losing 5,000 feet or a mile off the top of the volcano, and not just 1,000 feet. So these are huge eruptions, but that main difference being the collapse. So this is what I'm talking about. So here's Mount Mazama before, with a huge reserve of magma ready to go. It's ready to erupt. In those large eruptions, you're emptying out, imagine emptying out the top of that magma chamber, leaving a void. The top of the mountain then collapses into that void, and it leaves behind a huge depression, and that oftentimes fills with water, because like a lake. Yellowstone Lake exists in the same kind of way. But it's this collapse into the magma chamber, into that void, that makes the difference between a caldera and a crater. Okay. Hopefully that's clear. Here's Crater Lake again. Same idea, same sequence of events there to get you from the volcano to this. Wizard Island, this little island in the center, is what's called a resurgent dome. It's kind of like those lava domes were in Mount St. Helens and the other examples I gave you with the lava dome coming up in the crater. Last little bit of lava, same deal. So Crater Lake is actually misnamed, isn't it? It's not a crater, it's a caldera. It should be Caldera Lake, but it's not. Anyway, this is a picture of the giant pile of ash that was part of that eruption. Just to see, it's a huge pile of ash. If you were near that volcano when it erupted, you would have been buried, just like they were at Vesuvius and Pompeii, if you've ever seen those pictures. Okay. Actually, I've showed you, well, we just covered this, and we already talked a bit about these. So, oh, but I did add this video. So we talked about the amount of volatiles in different composition magmas. I'll let you go back and review that. But I did add this video. This is an experiment where I think this is a glass. Oftentimes we use glasses in experimentation because you can make a glass out of whatever you want, basically. This is a glass, you just melt your components. A glass that has volatiles, gases dissolved into it. And they're gonna allow those, they're gonna decompress it or take the pressure off of the container and let the gases exsolve into bubbles. Oh, I forgot, there's some rockin' tunes that go along with this. So you might need to turn your volume down. So there are the bubbles starting. I can't see how to mute it. Oh, there. There, I got it finally. Okay, let's look at it one more time. I couldn't find the mute button before. That's why. Okay, so check, they're starting to nucleate. They start at a point and they grow larger, larger, larger. So you can imagine, and then they start to grow together to form, they coalesce into larger bubbles even, until it's like a few giant bubbles. I'm going to stop it there. Okay, you get the idea. So if you were to remove the pressure rapidly, like a landslide in Mount St. Helens, those gases are going to exsolve rapidly and cause an explosion. Okay. All right. Magmatic differentiation. These are all, we're going to go just a bit past 12 o'clock today, but just a little bit. Okay. Not more than 10 minutes, if you can hang with me. All right. Magmatic differentiation. This is the term for any mechanism, and most of them are shown right here. Any mechanism that changes the composition of a magma. So this is like all the different ways that we can transform one of those basaltic magmas that you generate under a volcanic arc into an andesite or a rhyolite. I said that, you know, imagine this being a basaltic magma coming up from the Mantle Wedge. And it's joining a pre-existing magma chamber hanging out in the continental crust. It's got to get through all the continental crust before it can reach the crater, before it can be erupted. So I've got better pictures than this. I'll let this one just sit there because it goes into way more detail than I want. But it shows like pieces falling in, bits melting, crystals being joined. It's showing cracks forming and melt going into those cracks, that kind of thing. Here's some actual rocks that show what happens. These show partial melting. So we had a gray rock to start with. They're called a gneiss. We'll get to those on Tuesday. They're made, imagine a granite transformed into a metamorphic rock. That's what we're dealing with. That's what forms the gray rock. So you just mix all those minerals together on granite and it turns out sort of uniformly gray. If you start to melt that, right? If you start off with a granite and you partially melt it, what minerals melt first? Remember Bowen's reaction series? I said we needed to start at the low temperature end and move upwards. So it's those minerals at the bottom of Bowen's reaction series. So it's the quartz, the case bar, the muscovite, and then the sodium plagioclase. All of those minerals are going to melt first, and they all happen to be light colored minerals. And so all the initial melts are like white colored or light colored. So all these little stringers are it's like the rock is starting to sweat. That's how I describe it in my mineralogy petrology class too. It gets so hot that it starts to sweat, and it's giving off these little like stringers of really felsic melt. Okay, so you can partially melt a rock. And how do you partially melt a rock? You got to add heat. So if it's the rock around a magma body called country rock, if it's that host rock, you can start to partially melt it because the magma is hot. Another way we can change the chemistry of a magma is for crystals to actually settle out of a magma. And that's what you're seeing here. These layers are crystals essentially at the bottom of a magma chamber. So here's a magma chamber, way too simple to have a nice round magma chamber. It's probably more like magma filling pores and dikes and sills, etc. But the crystals settle, and it's probably some of those minerals at the top of Bowen's reaction series that crystallize first, because those are the ones that crystallize at the highest temperatures. They're also dense. They're mafic minerals. They're dense. They can fall through the magma and land at the bottom, essentially. That's what you're seeing here. So during cooling, you see crystallization at the highest temperatures. You imagine maybe olivines first, and then maybe pyroxenes next, and on, and that's showing felsic minerals, but you get the idea. One mineral after the other as that magma cools. If it's just sitting there, it could happen. Not always, though. If that didn't happen, then you just end up with the plutonic rock equivalent of the original magma. But this process that I'm describing is one that changes that composition, right? Okay, so I mentioned, I'm going to show you more pretty pictures, but this is like the graph showing the evidence of the chemistry. I've talked about, so look at the bottom, it's silica at the bottom going from 45 to 75%. So it's rhyolites on the right, rhyolitic magmas here, granitic magmas here. And then on the left are basaltic magmas or lavas here, okay? And what this is showing is like the evolution of a magma chamber over time, like the chemistry changing over time as material is removed, as eruptions take place, the remaining magma is different. So you might start off with a fairly mafic magma, and then over the course of the evolution of that volcano, it could become more and more felsic. And that's this line that you're seeing. So the blue lines show the trends of the chemistry for the mafic material, for the mafic magmas. They're high in iron. So at at 50% silica, they're high in iron. 50% silica, they're high also in calcium and magnesium, like I've been telling you. Turns out also titanium. But the felsic melts are rich in potassium. So 70% silica are high in potassium and high in sodium, and low in all those other components. Aluminum is a little more complicated. It looks like it hooks over like that. So I'm going to leave that out of this for now and just stick to felsic magmas having high silica and high sodium and potassium, and mafic magmas having low silica, having high calcium, magnesium, and iron. Okay, that's what I was trying to show here. Here's another pretty spectacular picture showing, a couple of pictures showing magma mixing or mingling. So if you've got like partially molten or mostly cooled melts, they might interfinger they might sort of flow together without actually mixing. If they mix, you would have like some average composition, right? If it's like stirred up and mixed together. But if you just mingle them together, then you see two different magmas. Here's a light gray magma, and here's a dark gray magma, these blobs, these pillow looking things. There's also a dike here, but that's not a separate magma body. That's simply a dike coming off of another melt. And this cartoon sort of shows two different magma chambers, two totally different sources. One is more mafic than the other. So the magma B could be the dark gray one. Magma A could be the light gray one. And magma B mixes in with magma A. And you might get mingling, but like I said, if they actually mix together, it would be some average composition. And then assimilation is that reminds me of Star Trek and the Borg. I'm not a geek or anything. So assimilation, you're bringing other rocks into a melt. So you're melting and adding that material to the composition of your pre-existing melt. So here's a magma, and here's the host rock or the country rock around it. And pieces are falling in off the roof of it. This is called, it has another term called stoping. You don't have to worry about that right now, but it might be large blocks like this one. How'd that get there? But this is a lot more felsic. It's like pink, like it's got potassium feldspars in it. So granitic compared to this much more mafic magma here. So a hunk of really different rock managed to get into this magma, and it looks like it's probably some process like this. Continental crust, a piece breaking off, being either ripped off the side of the magma chamber as the melt is intruding, or it can fall off into the magma chamber. So you incorporate these. This is called xenoliths. It's a foreign rock. If you don't know, like this is clearly a different magma, right? It's a totally different composition. If you didn't know that it was foreign, like maybe it's part of the same magma, we're not sure, it gets a different term called enclave. So if you're not sure of its origin, you call it an enclave. If you are sure it's a foreign rock, and then you can call it a xenolith. But again, you don't need to learn those terms as long as you can describe the process in regular words, right? As long as you can do that, I don't mind if you don't remember these terms, okay? Just describe these mechanisms that you can change the chemistry. Crystal settling. So what I show you? I showed you partial melting is one. Crystal settling is another one. Magma mixing and mingling is another one. Assimilation is another one. Okay, so those are a lot of different methods. Those are all shown in this diagram. And this also shows some other things. Don't worry about that so much. I just thought this was a nice visualization of all of those things together. Okay, last slide, I promise. And I think I'm going to do it in 10 minutes, like I said. All right, this is an important one though. This slide explains how do you generate melts? All right, and in this case, the basaltic melts that you get that are partial melts of the mantle. So if you partially melt the mantle, we've been talking about flux melting and decompression melting. Decompression melting in continental rifts and mid-ocean ridges, flux melting at subduction zones. And then of course, heat, adding heat will give melts off. So heat from the core is what gives us the melts that start at that D double prime layer near the core mantle boundary. Those rise through the mantle and then erupt through the crust at hot spots. So hot spots are an example of a melt that is generated from added heat to the mantle. Okay. Then let's look at decreasing the pressure first. Okay, so I'll try to interpret this diagram for you. All right, this corner up here is like surface conditions. So 0 degrees or surface, like 70 degrees Fahrenheit, you can imagine, and 1 atmosphere pressure. And then going down is like going deeper into the earth. And then going to the right is increasing temperature. Okay, the same thing on both of these diagrams. This side, the left side, shows solid mantle. So at cooler temperatures, it makes sense that you would have solid mantle. It's not molten, right? That makes sense. And that's true at low pressures and at high pressures. But at some temperature, you're going to start to melt the mantle, right? You got to increase the temperature to some point, you start melting it. That's this red line. So this red line follows the conditions. So lower temperatures at lower pressures and higher temperatures at higher pressures to melt that rock. Okay, that makes sense. So this is this would be liquid melts or melted mantle over here and solid mantle over here. So liquid mantle on the right, solid mantle on the left of the red line. The purple dot down here is like the mantle, a bit of that mantle wedge before sorry, not the mantle wedge, a bit of that mantle before the crust is thinned above it, before the normal faulting thins the crust at a continental rift, or before, or, you know, as the spreading at the mid-ocean ridge takes place. You're taking the pressure off of that mantle. What you're doing is simply moving the conditions that this rock is under up to here. You're decreasing the pressure. So it's like moving this purple dot from below the line. So in solid conditions at high pressures, you reduce the pressure by moving it up, and you cross that melting line. And so you can start to melt that rock. It doesn't melt all at once. It's not like it melts all in one go, right? It melts a little bit at a time. And that's why you end up with a basalt and not just melted mantle, like molten peridotite. It's basaltic. Does everyone get that? Right? Just a little bit of melting the mantle peridotite or pyroxenite, melting that rock just a little bit gives you a basalt, different composition. Okay, and that's by decreasing the pressure, you manage to cross that boundary that separates the solid from the liquid mantle, those conditions. So now you're at the same temperature, but lower pressures, you can start melting it. So this is decompression melting. You're decompressing, you're taking the pressure off of that piece of mantle. Get that? Okay, I'm going to move to the next one. I think there will be questions because this is not easy. Okay, here's another situation. Same deal. This is solid mantle here, liquid mantle on this side. Here's this red line this time. It's not the same red line, or well, this is the dashed red line is the curve if there was 0 water in the mantle. So if this is completely dry mantle, it melts at high temperatures, right? So at high temperatures, it starts to melt. But if you add water, you shift this line to lower temperatures. So the blue line are the conditions where melting can start if the mantle has water within it. So you're shifting the stability, you're shifting the melting point to lower temperatures. So where the rock, like if this is your piece of rock in the subduction zone this time, this is the, it says liquid here, but it would be solid. Okay, so the left side of the red line would be solid. The right side would be liquid. So it's sitting there in the mantle wedge solid. It's a solid hunk of mantle. But then you add water to that mantle and the stability line shifts. So the line moves to lower temperatures, and suddenly those rocks at the same conditions, same pressure, same temperature, can start to melt. Okay, so this represents this process, this flux melting process, where you add water to the mantle from the subducted materials, from the subducted crust and other stuff. Do these three mechanisms of generating basaltic melts, these partial melts of the mantle, does this make sense? This is definitely going to be on an exam. You're increasing temperature, like at the core mantle boundary with hot spots. You decrease pressure on the mantle and you can generate decompression melts, or you add fluids to the melt to get flux melting by decreasing the melting temperature of the mantle. Is that clear? Does anybody have any questions about how this works? This is our last slide, and it's good because my computer's about to die. I used up the battery. I've got 10%. I'm good. Questions? I'm surprised that this is 100% clear. Are you sure you don't have questions? Could you sketch a graph like this to describe these processes? If I were you, I would sketch these in your notes right now. I would sketch, you might even sketch a whole earth showing the core, the mantle, the crust, show where those melts happen at the core mantle boundary and coming up to the crust through the mantle for process 1. And I would put a dot on there. And the arrow is showing decreasing the pressure by thinning the crust on top of the mantle at these tectonic boundaries. And then this is by adding water, you shift that line to lower the melting temperature. Okay, so I want you to know the process that gets you the melts. So there are 3 processes. The different tectonic or not, I mean, hot spots or continental rifts aren't necessarily at tectonic plate boundaries. Okay, so the environment, let's say the tectonic or other environment where these processes take place, you should be able to sketch these within the earth. For your next exam, you ought to be able to sketch a profile of a mid-ocean ridge showing a thinner crust underneath the mid-ocean ridge, the spreading center, and showing the mantle coming closer to the surface to describe decrease in pressure. Or you should be able to show fluids coming off a subducting oceanic plate, entering a mantle wedge, and then lowering the temperature. So this is a big one. This would be a short answer question. So you might sketch this as your answer, or sketch it and annotate it. Okay, so I would be able to do that for your next exam, because this describes this one slide describes a whole lot of what we've talked about. So it's a big one. Okay. Please ask questions. I'm looking at the chat and I'm not seeing anything. Maybe you're just frantically sketching away. Okay. Tuesday, we're going to do metamorphism. It's going to be a brief introduction. And I'm, like I said, the lab will have the metamorphic rocks on it, but I don't expect you to start the metamorphic rock part until Tuesday, let's say. I mean, you can get ready for the metamorphic rocks by reading the chapter and taking that quiz before Tuesday, and then do the lab, do that part of the lab before it's due next week. I'll probably move the deadline to Sunday night instead of Friday to give you a couple extra days to finish off that combined lab anyway, since we're on a shifted schedule. I'm happy to answer questions. You guys are being real quiet. In fact, you know what? I'm going to grab my power cord and come right back. Think of your questions if you got them. Don't be afraid to ask. Or that's a silly thing to say. I know that it can be intimidating, and that my heart used to race before I was like getting ready to ask a question. My heart would pound and race, and I still get like that sometimes, believe it or not. Sometimes not. Sometimes I'm perfectly comfortable speaking in front of a group, and other times I get nervous. I don't know what it is. It's just your body reacts. So, I mean,
I have a question.
Yeah, go for it.
So is the Metamorphic Rock Lab pushed to next week, or is
So this week's lab, the one that I'm gonna put online shortly, like within an hour, I'm gonna put online today, is this week's lab, and that's gonna include igneous rocks and metamorphic rocks. Okay, so it's a combo lab, but there are only 5 metamorphic rocks on it. So that's why I'm saying, why not wait until Tuesday to do the metamorphic rock part? And you can, in the meantime, you can do the igneous rock part of the lab and, get ready for next week's lectures. So my goal is to try to catch us up by doing, covering metamorphic rocks on Tuesday and sedimentary rocks and environments on Thursday. And then I'll give you a sedimentary rock lab next week. Okay, so we're going to keep these rolling. Does that end? I mean, it kind of answers your questions. It's this week's lab and it's next week's lab.
okay? So this week's lab is combined with next week's lab.
Well, the igneous and metamorphic rocks are combined. There will be a new lab given out Thursday next week, which is sedimentary rocks.
Okay.
So the one I said, so this one that I haven't assigned yet. So right now you're finishing minerals, or done, hopefully. Igneous and metamorphic rocks, I'll give you until Sunday next week. And I'll put that deadline on iLearn, so you've got it. Just to give you a couple extra days, since this is arriving late in your to-do box. But like I said, it's kind of short, and I'm going to include some videos, or a video in your igneous lab too. Okay. Well, you guys, it feels like you're not asking questions. So you're either taking notes or you're waiting for me to like excuse you. You don't need to wait for me to excuse you, but you may be excused. I am done for today. So I'll see you Tuesday, losing track of the days. See you Tuesday. Have a good weekend. I will be here for study group tomorrow. So if you've got questions about the Igneous Rock Lab or the Minerals Lab, come find me tomorrow, 11 to 1. And yeah, I'll see you later.
Thank you.
You're welcome.
Bye, Mary. Sorry I stopped talking. I was just taking notes.
Oh, no. I figured I could see you taking notes.
Well,
or at least bending over to do something, which I figured was
yeah, I'm taking notes. Okay, well, you have a lovely weekend.
You too.
Bye.
Bye.
Actually, I have a question for the minerals lab.
Yeah,
Is it okay if I show it to you real quick?
sure. Let me stop sharing this. I hope, Marco, you were done with that. I mean, it's online too. Go ahead.
Yeah, I was good.
You were okay. Good. Thanks.
Of course. Thank you for the lecture, by the way.
See ya. You're welcome.
Bye-bye.
Bye. Okay, you can share anytime.
Okay. Um. Sorry, I have to go all the way down. Okay, so I've already started it, but I'm still having trouble on the actual experiment on the minerals. Like right here for the conducts electricity. How do you want us to find out how it
No, I don't want you guys to do that one. That's for the unknowns online.
Oh,
The unknowns online, he shows you the conductivity video. Right? You've seen those. At the bottom of the A01 page, he goes through these in order like this. He shows you a picture of the mineral, then luster, then hardness, then streak. And then at the bottom of the A01 page, he's got a video showing the electrical conductivity.
oh, see, well, that's also what I'm confused about. Like, is this supposed to be for the virtual ones or for the mineral kits?
Okay, you're starting with the virtual ones. That's the sample number on the left-hand side. A01, A02, A03, like those, right? So you need to do those completely first.
Okay.
And then what you're going to do is figure out which ones correlate to the ones in your kit. But you got to identify these first completely. So you got to go through, make notes on all the tests, go look at the chart, go look at the examples of other minerals, and then identify them, or at least try. Then you can look at the ones in your kit and compare.
Because I already like these ones that I did, these are actually the ones that I did in my kit, like
Okay, that's
actually
not the instructions. I put, did you get the version of the lab with the step-by-step instructions in it? Where I go like step 1, step 2, because if not, then you should go grab, I don't think you did actually. No, you didn't. Go grab the newest version online. Because I literally like step 1, go here, step 2, do this. And that will make it clearer to you.
they emailed it to us, right?
I think I did, but I just said go grab it on iLearn because I'm not sure if I did. I mean, I emailed you twice, so I don't know which version this is. That's why I'm saying go to the website, but okay, we can look. No, that's not the latest version.
Okay, then I'll go back to iLearn then. Here, lab 7.
Right there at the top.
This one?
Yeah.
Okay.
Okay. Now, this one is going to have, and there, right there. See, right, step 1, step 2, step 3, you didn't have those before.
Oh, I didn't. I thought I did. I'm sorry.
Well, oh, I mean, if you did, then okay, then you should follow those instructions. So you watch the videos, and then did you go to each page for each unknown and watch all the videos?
Oh yeah, I did. Yeah, I went to each
So you were
video.
supposed to take notes on the results of all those virtual tests on the chart. That wasn't meant to be for your known minerals, because you already, I mean, your kit, like you have an identification list. So I wanted you to compare, but I want you to identify these first, right? And then try to get those using those tests. But I want you to match the tests that you do on your own to the virtual tests. So you're going to still, I mean, keep your notes, keep that table that you filled out, because that's going to help you to identify those, right? But you need to do that for the unknowns online. So maybe just save the version of your lab that you've already started, save that. That's for your kit. And you can just keep that separate. You can turn that in if you want for your kit, and then start over with this new version and make note of all the results, the tests for the unknowns online. That's why it said like the sample number on the left, that was intended to, that was to tell you to go use those on that table.
Yeah, that's why I was confused, because it does say A1, A3, A0, but it also said like I thought we were supposed to do like the mineral kit as well, because it says like all these instructions are like right here, like don't put like do not allow like the HCI to.
Yeah, but read the instructions, read them in order, and then do them in order. Okay.
I did, yeah, I did.
Okay, then how could, I don't understand. Then you didn't make notes on the unknowns. You skipped over to the knowns. That's what I'm trying to say, is like you skipped all the unknown stuff. Or if you did it, you didn't write any notes down in your chart. You skipped that part.
Well, yes, I skipped the virtual part. Yes.
Yeah, that's what I'm saying.
Because I just didn't know where to put it, but at first, but you're saying to put it right here.
Yes.
Now, so we don't put the mineral kit right there.
No.
Okay.
I mean, what are those notes for anyway? You haven't even written the kit number down.
The kit number?
Yeah, like you haven't written down the number of the sample from your kit.
Oh yeah, because I just hadn't gotten.
How do you know what?
Sorry, like, I just hadn't done it yet.
So the one in the notes in your first row, I don't see where you've indicated which kit specimen you used. Right? Like
on which mineral or which?
Yeah.
Just which?
Yeah.
Oh.
Because you clearly picked up one of these and you did some tests on it, right?
Yeah.
So which one is the first row?
Oh, yeah, what it was,
Yeah, that's my point, is that you didn't write it down. So how are you going to know what it belongs to?
I guess I'll compare it to the mineral bank again, because I was comparing it to the mineral bank last night, and most of them, and it was like basically right again.
It was basically what?
And they were right for the most part. They were
okay. You're not understanding my question. So you did the tests and then you identified them and you confirmed it with the list. Is that what you're telling me?
Yeah, I did the test, and the mineral bank that you showed us, I was comparing both of them,
Okay.
both from what I got and both what's on the mineral bank. So then I matched what I got from here and what is on the mineral bank.
So you're matching. So you did this lab for your kit and compare this to the visual bank online.
Yes.
Okay. I'm glad you did the tests on your kit. That's fantastic. And I'm glad that it matched up and you got, and that if you did that, then put the specimen number, like, and write down which mineral you think it was. Right? There's no identification there. Like, go, like, fill this one out. Like, if you've already done it for your kit, get credit for it by turning this in, but you're going to need to put the number of the specimen. Like, there's a little number glued to each one, right? Like,
Yeah.
this one, it's right. It's got a little number on it. You need to put that in the first row, in the first column. You need to put that somewhere.
In this, oh no, this column, my bad.
Well, I mean, if you've done this for the kit, then you need to change it for the left column. Yeah. But you need to write it down is my point. Otherwise you don't know what's what, and you need to identify it as well. So if you already compared it to the mineral bank, then put the mineral name in there.
Okay. Wait, and we can't turn in this lab late, by the way.
Sorry?
We can't turn in this lab late like how we did with other labs, right?
If you need to, but like if it's just late, because I mean, it's the same rules as always, right? I have a deadline that I give you. It's technically tomorrow. I probably won't get to the grading for a while. So if you got it in over the weekend, it's probably okay. But the deadline's tomorrow at midnight. So try to get it done by then. If you can't do it, then take a little bit of extra time. But you're gonna have another lab to do.
Yeah,
So,
I know. Like I said, I'll try to get it in tomorrow.
Okay.
I just like I said, like I'm trying to like I have like work. That's why like I was trying to do it like the past few days when I didn't have work, but then I was like everything, and I'm always working nights.
Yeah. Well, so I give you those two, you know, if you get docked points or whatever, I mean, you do get the 2 freebie labs that are your low scores are gonna get not included in your final score. So you have 2 there that you can use if necessary, but try to turn things in on time. And I also said, if you can turn 10 of your 15 labs in on time, I will drop your lowest exam score. So that's another reason to try to turn it on time.
Okay.
So do you understand how to proceed with this one?
Yeah, you said to just finish what I was starting with the kit already, with the experiment.
Finish that off, sure.
And then watch all the virtual videos and photos that were on the website, right?
For for A01, and then you're gonna watch the videos and write a note down, whether it's metallic.
Write them all down like how I've been doing right here, right?
Exactly.
Just on a new piece of paper.
Right.
Okay.
Okay.
And when I just another question, when I do put the HCI on the rock,
HCl. It's an L.
HCl, sorry. HCl on the rock. What is the best way to put it out? Like, is it with cool water? Because it says cool water in the instructions.
You could, well, yeah, either like dab it with a paper towel or something, or rinse it under water. That's all.
Okay, because that's what I was doing last night. With
That's
I was
fine.
rinsing it under cool water.
Yeah, I mean, just a little bit of water. You just don't want the acid left on your specimen so that it gets on your hands, right?
Okay.
That's fine.
Yeah, I think that is about it.
Okay. Well, hopefully you can remember which is which, but I would get those specimen numbers from your box on this chart and write down how you identified them before you forget.
Mhm.
Okay.
Thank you. I probably will come back tomorrow too, just in case.
Okay. I'll see you then.
Thank you.
All right. Bye.
Bye-bye.